Titan is the second largest moon in the solar system. With a diameter of 5,150 kilometers, it is larger than the planet Mercury. Because Titan is essentially a sphere, with a formula for the surface area of a sphere, only by knowing the radius of a sphere, which is just the diameter in half, we can calculate the surface area. And it is around 83 million kilometers square for Titan, which is very similar to the surface area of Asia, North America, and South America combined. Titan is also the only other body in the solar system, besides Earth, that contains large areas of matter in a liquid state on the surface. Those are the lakes of mostly ethane and methane. Methane is used as a fuel source for some machinery, and there are even rockets that use liquid methane in combination with liquid oxygen as a propellant. Now, the reason that Titan has the ability to sustain these lakes is because of the thick atmosphere that it has and the temperature level. The atmospheric pressure on Titan very near the surface is on average about 1.5 bars, which is 50% greater than the pressure on the surface of the Earth, which means that it is quite a lot denser considering as to how much colder it is. Temperature affects pressure. The lower it is, the lower the pressure. But the current present conditions on Titan aren't perfectly static, and they have changed and are going to change. Just like nearly all of the objects in the solar system, Titan started existing around 4.5 billion years ago through the gravitational accumulation of particles that were a part of the disk system of our Sun when it was still newly formed, specifically as a part of an accumulating disk part of Saturn, which is why it has the typical non-captured orbit traits. Through methods of dating rocks from the moon and meteorites and other objects in the solar system, we confirmed the year of formation for the objects in the solar system to be going back to 4.5 billion years. Although some surfaces, because of geological activity, can be younger than 4.5 billion years, which is the case for Titan, but it still certainly did exist around that time. Now, the drastic changes that have happened to Titan over the course of 4.5 billion years and are going to happen in the future are essentially set off as a result from the changes that are occurring with the Sun. But such changes are very subtle over a short time span. I'm talking about the fact that the Sun in the core, because of gravity, extremely high temperatures, and quantum tunneling, is fusing hydrogen into helium. There are also other fusions occurring that also release energy. The process of that happening generates, or better put, releases energy that eventually reaches the objects of the solar system. But as that process is happening and more hydrogen is fused into helium, the density of the core begins to increase as the total number of atoms drops. Then because of that, fusion in the core drops as there is less hydrogen there, and then there is less heat pressure resistance of gravity, which causes a contraction of that core, and that increases its density. Then as the density of the core is increased, that causes an increase in the rate of fusion of hydrogen, as the more pressurized surface of the core causes more fusion to occur. And then there is an increase in the Sun's energy output, and with that there is a greater level of luminosity radiating from the Sun as time goes on. But that also poses a big number of questions as to what happened in the past on Earth. So almost certainly, based on the Sun's trend of increasing luminosity, that also implies that in the past, around 3 billion years ago, it was much less luminous. Enough so that the distance at which the Earth is at from the Sun is where the temperature was too cold for liquid water on the surface. And yet we have evidence of life, and with that, liquid water existing around 3.5 billion years ago on Earth, and it was likely present way before that. One of the suggestions that solves this problem is by saying that it is because during that period there was a greenhouse gas such as carbon dioxide present in very great quantities in the atmosphere, which maintained a level of temperature which allows for liquid water to exist on the surface. And then the CO2 levels dropped as more complex organisms developed that interacted with that CO2 and lowered it. Or it might have been just the case that liquid water existed under the frozen surface water ice, where through geological activity that water was heated, and that is where life was 3.5 billion years ago. But this is a bit besides the main point, although it is still connected to the question of Titan's future, but also the past. So because the Sun was much less luminous far in the past, that also tells us that Titan, around 3 to 4 billion years ago, on the surface was colder than it is today, almost certainly to the point at which methane and ethane couldn't have been in a liquid state. So that would mean that the surface temperature was not the minus 170 to minus 180 degrees Celsius that it is today, and it was more likely around minus 220 degrees Celsius, similar to the current surface temperature of Triton, moon of Neptune, which is 3 times farther away from the Sun than Titan. So because the temperature was not adequate for liquid methane and ethane, there were no lakes on Titan 3 to 4 billion years ago, unless for some reason Titan kept the same level of temperature by having significantly more greenhouse gases than today and a similar atmospheric pressure. But that is unlikely to be occurring with such a low amount of luminosity from the Sun, and nearly no way of explaining how the greenhouse gases went away later. And it is just way more likely that during that time it just had a much thinner atmosphere, as the luminosity was low enough so that the temperatures were enough to freeze most of nitrogen and methane as soon as it was on the surface. So it likely had a much more naked look. The atmosphere was possibly in ways similar to current Pluto's, where it is overall very thin, but there is a layer of nitrogen and methane that has an elevated temperature. But of course most of nitrogen is still frozen at that point, it's just that a bit of it won't be. So that would mean that although the atmosphere on Titan wasn't adequate in temperature and pressure on the surface during that time for liquid methane and ethane, it was still visible to some degree. And because of the magnetic field protection from Saturn and the stronger surface gravity, it was still likely quite a bit denser than the current Pluto's. But as the temperature elevated enough as the Sun's luminosity increased, and it elevated to around minus 190 to minus 200 degrees Celsius, that is likely around 2 to 1 billion years ago, then it very likely did have a very thick atmosphere during that time, and surprisingly, it was quite possibly even a bit denser than it currently is. There is a model made through studying comets, which are essentially partial building blocks of spherical objects in the solar system, and the model suggests that the atmosphere is coming from Titan's internal structure. And because the internal structure, and with that certain molecules that have nitrogen formed with Titan as a part of it, then through tidal forces, that is gravitational pulling of Saturn and its other large moons, the structural material is cooked through friction and then outgassed to the surface. So because during this time, around 2 to 1 billion years ago, the temperature was enough to allow large quantities of nitrogen to exist in a gas form and not be frozen, and the temperature is not as high as it is today, the atmosphere then was quite possibly even denser to some degree than it is today. That also at a certain point could have allowed for lakes of liquid nitrogen to exist, as the pressure and temperature was at a point at which it could have sustained a chunk of nitrogen in a liquid form. Now the much slower nitrogen gas, which currently makes up about 95% of Titan's atmosphere, and very likely in similar measure did back then, had a harder time during that period of escaping from Titan's relatively weak gravitational pull, allowing for a great buildup of nitrogen near the surface, and then an atmosphere that is possibly even denser than the one currently present. During this time, 2 to 1 billion years ago, the significantly lower luminosity from the Sun made Titan extremely dimly lit as well. Certainly the significant features that it has now, if they were even present then, were shaped differently, as the geological activity shaped the surface of Titan, certainly at a minimum, for a billion years or so, since there is very direct evidence for that, and the surface was very likely molded for its entire lifespan, as there were tidal forces necessary for that to happen all throughout. So overall, its general look was different. The lakes of methane and ethane during that time were non-existent, as the evidence suggests that the temperatures were also at that time low enough for methane and ethane to be frozen, but as I already said, quite possibly enough for liquid nitrogen. Now the reason that Titan's surface evolves in general, as in it has a surface layer that is being constantly molded, is because of geological activity. So Titan's surface has a very low amount of impact craters, suggesting that it is around 100 million to a billion years old, which since it existed for 4.5 billion years would be very weird, unless of course there is some form of geological activity that erodes the craters over a certain period of time. That geological activity could be due to a sort of a tectonic movement which could be because the top layer of Titan is floating on a liquid ocean of something, likely water. Similar to the mechanism of Earth's tectonic movement, except the top layer of Earth is instead pretty much floating on liquid rock, which then leads to an erosion of craters as movements of the top floating layer happen. Now on Titan, there could also be an eruption of ice going on that successfully covers the craters over a period of time, which could be a result of, again, friction that tidal forces can create and a subsurface liquid layer. Then as we move forward into the future, very slowly as the luminosity of the sun is increasing over hundreds of millions of years and the surface temperature of Titan is rising, and with that the brightness and visibility is increasing on its surface, the very possible lakes of nitrogen evaporated, and the relatively huge amounts of hydrocarbons, that is methane and ethane, and some propane, turned, and some that were in ice form melted into liquid, and a portion turned and stayed into gas as the temperature on Titan reached around minus 170 degrees Celsius, and created relatively big lakes and rivers on the north and south pole. The vast majority of the lakes are there because there is less direct sunlight there, allowing them to exist and not evaporate. The first confirmed lake made out of hydrocarbons is Ontario Lacus. It was confirmed through a spectrometer attached to the Cassini probe in the June of 2008 that the lake was made out of liquid ethane, methane, and propane. Cassini also managed to capture a big reflection off of the lake Ginkgo Lacus in 2009, adding on to more concrete proof of their existence. By now there are nearly 90 confirmed lakes of over 10 kilometers in length, most of them located on the North Pole, and they can be as shallow on average as a couple of meters, such as Ontario Lacus, a huge 20,000 kilometer square lake, and there are some that are reaching depths of more than 200 meters, such as Ligeia Mohr, that is even bigger and is the second biggest by surface area at 126,000 kilometers square. Now, although most lakes are on the poles, there are still a few lakes along the equator where it is mostly a desert. They are likely there due to aquifers that keep those lakes intact and not evaporated, although a more appropriate word would be something like methanifers and ethanifers. As the time passes over billions of years and the sun's luminosity increases, the surface temperature of Titan is as well going to rise, causing a gradual evaporation of its lakes. Then there will be more and more methane in a gas form through evaporation building up in the atmosphere that will have a big greenhouse effect. The atmosphere will very likely visibly be not as dense. The pressure will be lessened to a great degree because it will be easier for the gas to escape from Titan's weak surface gravity because it will have much more kinetic energy. Some amount of an atmosphere will certainly be there, but to a lesser extent. This should all be apparent 1 to 3 billion years from now. Other interesting changes are that the rings of Saturn very likely won't be visible at all through a diminished, much less obstructive atmosphere of Titan, as even at the moment, Saturn is losing its material from the rings at a relatively fast rate, so Saturn from Titan will look like any other gas giant. The visibility of the surface will also be higher due to greater luminosity from the sun. Now, the reason that Titan is able to hold on to an atmosphere at the moment with such a low surface gravity, while a bigger Mars with a surface gravity nearly 3 times greater has an atmosphere that has a pressure on the surface that is around 250 times less, is because Mars doesn't have a magnetic field and Titan is shielded under the magnetic field of Saturn, which protects it from the harsh solar winds to a degree that its atmosphere isn't stripped away yet. But another significant reason is simply because the temperature of the atmosphere of Titan is very low at around minus 180 degrees Celsius, so around 3 times colder than Mars. This means that the molecules in its atmosphere are moving at a slow pace, so not a lot of gravity is required at those temperatures for the gas molecules to be held near the surface. There is even a place like Pluto, which has a surface temperature of around minus 230 degrees Celsius, but still has an atmosphere. It's thin, but it's very much visible. While the Moon, our Moon, has a surface gravity 2.5 times greater than Pluto's, but it doesn't have one. There are possibly other better comparisons, but essentially significant atmospheric escape is very much possible with the huge chunk of molecules have a molecular kinetic energy that is greater than the gravitational energy, and the greater the temperature of the atmosphere, that is kinetic energy, the more molecules get to achieve escape velocity, which causes atmospheric escape. So the main reason that Pluto does and is allowed one essentially is simply because it's extremely cold, enough so that the gas molecules are held near without a significant gravitational force, and even without a magnetic field. So as the millions of years pass and the temperature increases, the kinetic energy of the molecules in the atmosphere is also increasing, causing a significant chunk of them to escape from Titan. Again, it's hard to tell how much there will be atmosphere left 3 billion years from now. It very likely will even exist at that point, but it won't be quite as dense. It could be 1/3 the density or even lower. At around 5.5 billion years from now, the Sun will reach the red giant phase. The observations of stars of the similar mass to the Sun allow for us to make these extremely powerful predictions. Essentially, the stars of the same mass as the Sun always display a predictable life cycle. They always go through the nearly exact same stages. Most stars are actually fairly simple in composition, with most of them, when they start existing, being 25% helium and 75% hydrogen. Because of that, depending on the mass, the physical laws will act in a linear fashion with that composition and mass, and with that, there are predictable stages of stars. That is why when there is a star of the nearly same mass and age as the Sun, it's also the same in luminosity, surface temperature, and its diameter. So when there is a star of the very similar mass to the Sun, that is around 5.5 billion years older than the Sun, then it is in the red giant phase. That is when the core density reaches a critical point at which the weight of the layers above the core crush it enough so that the electron-degenerate matter is formed in the core, which causes a drastic acceleration in fusion and a greater level of increase in luminosity. Because of the much greater energy release that will cause, that will also cause the outer layers of the Sun beyond the core to inflate drastically. It will be such an enormous expansion, such that the whole diameter of the Sun will reach around 300 million kilometers. That will certainly be enough to engulf Mercury and very likely Venus. As for the Earth, even factoring in the loss of mass from the Sun and the distancing of the Earth's orbit that could cause, some calculations strongly suggest that the Earth will also be engulfed. If not, then it will certainly be a scorched planet with liquid aluminium and copper. At that point, the Sun's luminosity will be many times greater due to the massive surface area that it will have, and it will get to the point at which it will very likely turn the surface temperature on Titan to the level at which water turns into liquid at 1 bar pressure, that is to say, beyond 0 degrees Celsius. But by this point, it is nearly certain that Titan's atmosphere will be a lot thinner, or just thinner to an extent due to the temperature and its gravity. Pretty much a huge chunk of it will be gone. It will be a lot more bare. Very likely, the haze that it has right now won't nearly be as pronounced, and the surface features from space will be visible clearly. Still, Titan will have a magnetic field protection from Saturn even 5 billion years from now, which can help greatly for Titan to retain a relatively dense atmosphere. Even if it happens to be the case that the atmosphere is 20 to 40 times less dense than it currently is, and the temperature is very roughly stabilized at around 10 degrees Celsius, that could very much allow for the lakes of liquid water to exist. And in that scenario, they very likely will, as the temperature will melt the water ice on Titan's surface. Then, the only solid thing left will be the hydrocarbons that melt at relatively very high surface temperatures of around 300 degrees Celsius. So there is actually quite a large window of opportunity for liquid water to exist in both pressure and temperature range, which is why the future of Titan, where it has lakes or even bigger oceans of water, is actually a very much possible future scenario. However, if it happens to be the case that the temperature established is far too high for liquid water, under the established pressure, the water ice will simply evaporate, and very likely, in that case, since water vapor is a greenhouse gas, drive the temperatures even higher and drive the atmospheric escape further. If it happens that the atmospheric escape of Titan is far too great, such that the density of it is something like 500 or 1,000 times less than it currently is, then no matter the probable temperature ranges, the density of that atmosphere in that case is far too low, so any likely pressure that could be established in that case won't be enough to sustain liquid water for long. Still, considering how dense the current atmosphere of Titan is, there is quite a lot of room for plenty of atmospheric escape and for liquid water to still be established under a relatively large temperature range. Plus, on top of that, the atmosphere is regenerated, as already mentioned. However, the scenarios in which the criteria aren't met for liquid water are also very much possible. Now, whatever the actual future scenario is, as the atmosphere will very likely in all of them be so diminished, the red giant sun will appear huge from Titan, even accounting for the distancing that will take place from its center. It will appear around 2 times bigger in the sky than Saturn does. That is around 20 times bigger than how the moon appears from Earth. As the calculations show, the Milky Way and the Andromeda Galaxy will also be colliding roughly around this time as well. That will cause the sky visible during the night on Titan to take on a different look, but almost certainly there won't be disruptions to the solar system by collisions with some stars from Andromeda, as the usual distances between stars of a couple of light years are far too great for that to be likely at all. Now, whether it will be a lively Titan with liquid water or a much more barren, cold or hot Titan, as the red giant phase of the sun can last from a couple of tens of millions of years to 2 billion, Titan will ultimately end up in a similar place at around 7 to 8 billion years from now. When the sun reaches a critical point in fusion acceleration, it will shed its outer layer, creating a nebula. That shedding, when it is happening, will be visible from Titan, but will for sure be a spectacular view. But that also means that the sun at that point transitioned into a dense white dwarf that is not undergoing fusion anymore. It is releasing stored energy. Its volume will be about as big as the Earth's, although its mass will be many hundreds of thousands of times greater than the current Earth's. Because of that, this change will have an effect on Titan. As the surface area of our sun will be so relatively tiny, it is comparable to Earth, it will be very dim from the distance of Titan, causing the surface temperature to go down drastically, likely to around minus 230 degrees Celsius or even much lower. Then on Titan, it will be extremely poorly lit. The sun will appear during that period as a dot in the sky. It will pale in comparison to what it was. Here the future of Titan should be relatively similar no matter what happened during the red giant phase, as the temperature dips to minus 230 to minus 240 degrees Celsius because of the low luminosity from the sun. So not only will most of the methane be frozen, but a huge chunk of nitrogen that was a part of the atmosphere will also be completely frozen, creating a surface layer of nitrogen ice. So the atmosphere will be similar to how the atmosphere was likely like on Titan shortly after it formed, as the temperature conditions will be similar. So it will be a thin but also visible layer of nitrogen and methane that is regenerated and stabilized because of outgassing from the internal parts. Likely at that point there will be still geological activity, because tidal forces will still be there and a floating top surface layer. So the surface will likely be relatively smooth at that point. It will lack many craters like it does today. Now, because the white dwarf is emitting stored energy, it is also running out of it. So as the billions of years pass, it will emit even less and less light. The lifespan of a white dwarf is not known, and there is not a single known one which has reached its end stage, which is at the moment a theoretical black dwarf that is solidified and crystallized after it used up all of its stored energy. Some estimates say that this stage is reached after the current age of the universe has passed multiple times, so tens or hundreds of billions of years, possibly a trillion and more. So as our sun in the white dwarf phase approaches the black dwarf phase, the surface temperature of Titan will also drop near the absolute zero. Of course, not the absolute zero though. Because of that, any possible atmosphere on Titan of nitrogen or methane or anything else, no matter the density, will nearly completely freeze up. The atmosphere will solidify. This far into the future, it is a nearly dead barren land that is extremely poorly lit. Possibly due to tidal forces, there could still be a level of geological activity, so some remolding of the surface could bizarrely still occur at that distant point in time, but it's hard to tell. Eventually, when it gets to the point at which all of the energy from the sun is used up completely, the surface of Titan will reach a near pitch black. Only the photons from stars light years away will be reaching the surface, which won't be sufficient to make the surface visible to the naked eye, although the view of the sky from Titan at that extremely distant point in time will likely be great, assuming that there are many bright shining stars left that far into the future.